Today, I'd like to introduce a multiple L function associated to modular form. It's an analogy of multiple zeta values. So title is multiple L function of modular form. So multiple zeta value, say zeta k, zeta k. I don't like the definition, but this value is defined by multiple Dirichlet.
What's the order?
Today I don't mind, but you will see
Okay,
soon
okay.
later. Multiple sum. And then this real number has an expression in terms of iterated integral. On the other hand, in number theory, we are interested in the L function associated to modular form. L function associated to modular form. Well, precisely speaking, only we treat Casper form today. Is denoted by L, F, S. Here S is a parameter, complex parameter. And this is defined by Dirichlet series of this form. I will explain the details soon later, but F is a Casper form. This function is defined on the complex upper half plane and period 1. So this has a Fourier expansion. Using a Fourier coefficient, we will define L function. So numerator, you will see the Fourier coefficient of modular form. Nice thing is this function on S has an integral expression of this form, some minor factor times 0 infinity fc c s minus 1 dz. Here f is a Casper form defined on the complex upper half plane and multiply this type of integral kernel and integrate along the path connecting 0 and infinity on the complex upper half plane. This type of integral is called Mellin transformation of f. So roughly speaking, L function is given as a Mellin transformation of Casper form itself. And this factor contains a gamma function and also power function of pi. I will write down exact form soon later. So by comparing these two concepts, what I want to introduce today is a multiple version of L function. You will see a multiple Dirichlet series, and the numerator, you will see the product of Fourier coefficient. And my first aim is to generalize this identity. Okay, let's start. So today, first I introduce multiple L function associated to set of Casper forms and generalize this identity to the following form. So in the classical identity, left-hand side is the L function, so you will see the multiple version, multiple L function in left-hand side, multiple L function. And the right-hand side is replaced with the iterated integral of Casper forms. Actually, this type of integral, iterated integral of Casper form is studied by Manning around 2004. So right-hand side is already Manning. Wrote two paper or report related to this integral. This is my first aim. And one of the main goal or main interesting topic for multiple data value is to consider the algebra generated by all multiple data values and consider the algebra structure of them. So we will follow the analogy of the story. So first consider the space spanned by multiple L values, special value of L values, and it has algebra structure we can show, and what's the algebra structure of them. So second topic is on the algebra structure generated by special value of multiple L functions. So we just call multiple L values. Okay, so here is the outline of this talk. So I will start from the basic notion of CASP form. And L functions. So CASP form I mean today is a traditional one. So this is a holomorphic function on the complex upper half plane. So usually we denote H upper half plane. So this is a set of complex number whose imaginary part is positive. So this way. CASP form is a function on this region, and we require some symmetry on CASP form. So I skipped. Sorry. So a CASP form. F is a complex valued function defined on H. And this is a holomorphic, and I want a more precise definition. So CASP form F of weight K and level N, where K and a positive integer is defined. This is a holomorphic function. So first requirement is this is holomorphic and satisfying this relation. Where ABCD is a matrix determinant 1, so I define the set of matrix gamma 0 n is a 2 by 2 matrix. All entries are integer and determinant is 1, and this C part is a multiple of n. It's easy to check. This set makes a group, subgroup of S to Z, and usually we call Hecke group of level n.
I've never heard Hecke group.
Hecke group? Ah, really? I find the name.
There's a well-known Hecke group that's called the Hecke group that's completely different. So.
Ah, really?
But this is probably also Hecke group.
Yeah.
I think it's usually maybe it's called.
Ah.
Anyways, it's really his group, yeah.
Mm-hmm.
Hecke's group.
Yeah. This is the first requirement, holomorphic, satisfying this condition. And I didn't say, so SL to Z or any subgroup acts on the upper plane by linear fraction. So we require this type of symmetry on gamma 0 n. And the second condition is called CASP condition. Second condition for any CASP. Here, CASP means rational number or infinite point, I infinity. This is a boundary point of H. We require CASP form go to 0 exponentially, so decay, CASP form decay exponentially. When parameter approach to CASP. This is a definition of our CASP form today. And one of the interesting property is if you input A, B, D is 1 and C is 0, then this identity says F is periodic of period 1. So F has a usually since F is periodic, this has a Fourier expansion C1q plus C2q squared of this form, where Q is exponential 2 pi I z, where z is a parameter on the complex Kaplan plane. So Q is a fundamental unit of period.
Usually, surely always.
Usually we express. You mean that?
But I mean, this expansion always exists. This is not. I mean, usually it looks like you mean that usually you have such an expansion, but there's some exception. But there's always such an expansion.
Usually it's written in this way.
You just mean usually you'll call these numbers Cn.
I mean, so from this definition, it's easy to imply this one. Usually we express.
Okay. Now I understand.
We're using this expansion. And the number theory is interested in the arithmetic property of these Fourier coefficients. And this is a notation. So today, Skn is a space of C vector space of CASP form of weight k and level m. Weight k and level m. Example, one of the famous example is Ramanujan delta function. This is defined by infinite product of this form. If you write the quotient tau m, then lower term becomes this way. Q negative 24 Q squared plus 252. Okay. In general, Fourier coefficient is a complex number, but in many interesting cases, the modular form has a rational coefficient or integer coefficient. This is an example. CASP form has an integer coefficient. One of the interesting property of this Fourier coefficient is following. For example, we can prove tau has a multiplicative property when mn is coprime. And also, this type of recursive formula holds. The coefficient of p r to the n, p the prime, is written by negative p to the 11 times p sub p, no, r minus 1. For any prime p, and for any positive number r. For example, when p equal 2 and r equal 1, this fourth coefficient is given by the square of second negative 2 to the 11. I think it's true. So this is an example of arithmetic property of Fourier coefficient. Using this Fourier coefficient, we define the L function. So for given any cusp form, we define L function by this way, where S is a complex parameter, but to guarantee the convergence, the real part of S should be large enough. I think this is k minus 1 is enough. And the important formula is this function is expressed as a Marin transformation of the cusp form, as I said before. So 0, I infinity, that is d s minus 1 dt. It's easy to prove if you substitute this Fourier expansion to f, then integrate term by term gives this expression. There are some gamma factor appears and power function on pi, and last part is L function. And the key point or important thing is left hand side is defined for arbitrary s. So from the cusp condition, this function decays exponentially when parameter z tends to cusp infinity or 0. So this part goes to 0 rapidly. So even though you multiply such polynomial factor, this is enough, too small. So this integral converges for arbitrary s. But the right hand side, L function is defined for some right half plane. So using this expression, we can do the analytic continuation of L function. So one of the direct consequences, analytic continuation. So there are no pole, the entire function appears. And if you look at more carefully, you can find some symmetry that S, some symmetry on Ls and Ls k minus s. It's called functional equation. Today I don't use that fact. So this is one of the most fundamental expression of L function. Today I want to generalize this one. So you will see the iterated integral instead of this expression, and right side you see the multiple L function. maybe second session is about to introduce the multiple L function. The classical case, for given one cusp form, we define L function, but to multiple case, we prepare set of cusp forms. This symbol means F from F1 to Fn is a cusp form of weight k and level n. For given set of cusp form, we define, and also we need a Fourier coefficient.
You want them altered the same way.
Actually, to define the following, I don't need just
You will want it later.
yeah, just I need a Fourier expansion and the cusp condition. First, I define iterated integral. So actually, this object is defined by Manin. Here we have n complex variables. And the second line is the data of cusp form is defined by one F2 V2 V2 is 2 minus 1 2. You should compute this iterated integral from right side. First, you integrate this factor in Vn along the path connecting infinity and some variable on the complex upper plane, Vn minus 1. Then, until here, you get a function on Vn minus 1. And multiply the second factor and then repeat this procedure again. Then finally, you should evaluate. You integrate along the path connecting infinite and 0. From the cusp condition, this iterated integral converges for arbitrary complex numbers. So its entire function the definition.
Is it Manin's integral? Is it called Manin's integral?
I don't know the name, but Manin defined.
Oh.
Manin. Around 04, he wrote 2 papers. He considered the analogy of associator using this type of integral. Next definition is for multiple L function. I use capital L. This is also n variable function. So I'm using this order. And denominator is S1, S2. You see the Fourier coefficient on the numerator, but please care the subscript n plus 1, and here n plus 1 is just 0. This is definition of my multiple L function. So we have 2 choices of L definition of multiple. So one of them is here, and also you can define another multiple L function by replacing this is just a CM1 and CMN. But in this talk, I only consider this type of L function. And this function is defined if every real part of every each parameter is large enough, then it converges. Or more strong, we can prove more for fixed. If you fix S2, Sn is a fixed positive number, then if real part of S is large enough, then it converges for fixed parameters. Analytic continuation of this function is not trivial, but Matsumoto Tanigawa gave analytic continuation extended to an entire function on n-dimensional space. This is result by Matsumoto Tanigawa. (2003) using analytic method, Marine-Barnes method or something.
That's Koji Matsumoto?
Koji Matsumoto, yes. My question is, we have two multiple variable functions. Are they related? Answer is yes, as they are related as a single variable function, not n variable function. This result is by Yeonju Choi and me around 2010. Actually, the relation of these two functions is very complicated. So just I want to show you when n equal to 2 case. So now we have two variable functions. L function here, first parameter is complex variable, and the second parameter is fixed parameter, fixed positive integer. This function can be written as a linear combination of iterated integrals. We have gamma factor, two gamma factor here, but here alpha is just an integer, only s is a parameter, and pi factor 2 pi I power is alpha plus s, and the last part is sum of L. I'm sorry, something strange. I'm sorry. Left hand side is iterated integral. So this expression gives iterated integral is expressed by sum of L function. Sorry. So here is L. Express j minus 1 j. Here is binomial coefficient. J alpha minus j f1 f2. You can get a similar formula. It means description of L in terms of sum of iterated integral. So we have some kind of inversion formula. So this is a special case. But you see, when n equal to 2, we have single sum. But when n equals 3, you have a double sum. and the coefficient, in the coefficient you see the product of binomial quotient, and so combination is very complicated. So today I want to show you the simplified statement. It simplified the statement much more, and also proof becomes almost trivial. Yes.
Yeah. Is it possible to extend this alpha as a complex number? Then
At this moment, no, and also I don't expect.
Because then this is some
Yes, it's nonsense.
Infinite sum.
Yeah, at this moment, I don't know the result, and I don't expect this is, I think, it's the best possible result, I think.
Well, it might be true with an infinite sum, but it wouldn't be so useful. I mean, the finite sum is.
Because
It's equal to arithmetic.
But this equality holds all for all positive.
All
integer.
positive integer, yes.
So
Probably it does extend, but it won't, if it's not finite, it won't be useful for arithmetic purposes. So it seems not very useful. I
Mm,
mean,
Yeah.
even if it's true, because it becomes an infinite sum, so how
mm.
it wouldn't be.
So at this moment, I don't know the
I mean, it's
generalization of this expression.
Every function is an infinite sum of every other function.
So next is simplified formula. Okay. It's better to keep these two notation. So
We're taking notes.
is it okay? For a while, for a while.
one more question.
Yes, yes.
This if n is equal to 1, and then this is iterated in many transform is equal to a function. This
Yeah.
is
It's a traditional.
And to show this equality, it is not necessary to assume that f is automatic function. It is equal
Yes.
for any Fourier
Yes.
function which has Fourier expansion.
Actually, we don't need a modular property.
Yes.
So
Is
to
it
define
question?
iterated integral, we only need a Casper
Yes,
condition.
yes.
And to define the L function, we only need a
Yes, yes.
gross condition of Fourier coefficient.
Yes,
It should be
Yeah.
polynomial order.
Yes.
Then
How about this equality? This equality.
we don't need a modular
You don't
property.
need,
So actually, sorry.
Modularity has not yet been used, is what you're saying. So far, it's just Fourier expansions.
Fourier expansion and
If-
gross condition of Fourier coefficient.
But how about, I mean, in the one variable case, of course, these functions, the main property is not just that they're equal, but they have a functional equation. And that is the modularity. Is there something?
Yes, functional equation, to imply the functional equation, we need a modular
Is
property,
there,
but
is there also here a functional equation? Will tell us?
no. But Manning considered, if we consider some correction or some generating function of L function, it has a functional equation. But for each L function has no such symmetry.
So, actually, you haven't given yet any motivation, except that Manning is very famous and he wrote it down. But why does one, in the classical case, you write it down because it first of all has Euler product, which certainly
Yeah.
and secondly, there's a functional equation. And so that's a wonderful, I mean, that is very important number theory, function,
Yeah.
Euler product and a functional equation. And Hecke found, of course, that L of Fs does it. Do these have any?
No.
Properties like that.
So what is here is similar to multiple data values, no Euler expression and no symmetry implication. Okay. So we introduce a generating function to simplify that result. So generating function has a coefficient, this type of whose power series whose coefficient is iterated integral. A second generating function has a quotient of multiple function. So let me write down the precise definition. So just before I write this definition 1, so this is the generating function version, so f1 prime. So only first parameter is complex variable, and the other parameter is sum up. Here x is just a formal parameter, small enough. This is I, script I. I define the following power series. Exponential 2 pi ip1 x1 s1 s minus 1 t. Exponential 2 pi ip2 x2 ep2. IPN xn TPN. This is the definition. Only first factor has this kernel of Rayleigh transformation. If you expand this part, Taylor expansion of this factor, you get a polynomial in D1. So it's easy to see this is a generating function of previous function. Precise form is here. So if we specialize, so this is I 0 if you compute this function, then you see the previous iterated integral in the coefficient. Here, alpha 2.
S equals 0, or did you just leave out
This
the,
is
the S, the last, the variable S that you've introduced here?
ah. Thank you. Thank you.
So,
S is a sum of some pi factor alpha 2 alpha n minus n plus 1 and iterated integral s alpha 2 alpha n f1 n. This is the alpha 2 minus 1 factorial, so it's a kind of exponential type of generating function. And similarly, we introduce a generating function whose coefficient is multiple L function. And we look at, we compare the two generating functions. The definition, 2 prime. For complex numbers whose real part is large enough, and here y is a parameter of power series, which is also small enough, then we define the generating function of multiple L by this form. Numerator is exactly same as previous one. And denominator changed to this form. The only first factor has a power s, and the other power is everything 1. It's a kind of generalization of Hurwitz data function, like shift the parameter a bit. If you expand this expression in each variable y to yn, then you see the multiple L function in the coefficient. So this is a CF. L function, first variable is 0, and y2, y1, f1, fn, s. The same.
The last sum, mn minus mn plus 1 is it? Mn doesn't appear here, so.
Here, this one. Thank you. It is 0. You mean this one? Okay, thank you. Same sum, and no pi part, just plus n minus n plus 1 L function. No. This is normal type, generating function normal type. You can check easily. Now we introduce a two generating function. The relation of two generating function is quite simple. So here is the theorem. For any complex variable s whose real part is large enough, then left hand side is iterated to integral. On S. And right hand side, I didn't explain. I just follow the Manin's setup. So today I use the infinite point as a base point of integral. So 0 is also natural choice, but I just follow the Manin's. So this factor -1 to the end, this factor appears for this choice, and the gamma factor. And what is the pi factor? Minus pi to pi r. S plus n minus 1 and L y1 in f1 fn s. This holds where x and y relate naturally. y1 in 1 1 1 0. No. This holds. So this is a natural, I think, natural generalization of classical formula. So you see the iterated to integral left hand side, and right hand side you see the multiplier function.
And y and x are small.
To define this one. So you see this is the q to the x1. So if you look this one, if you consider the full expansion of this part, the first there are no constant term, right? But if x1 is, for example, negative, largely negative, then the pole appears here. So to ensure to guarantee the convergence, the x1 should be small but positive.
By counter-relative. So the
When
imaginary part is bigger than
yes,
multiple
so
scientific.
near infinite point, no, it should not be constant term, right? So x should be positive or positive but small. And to check the convergence around 0, so let's say we need to transform 0 and infinity using fractional transformation. Then for both cases, x1 should be, let's say, small and non-negative. Actually, we can relax this condition a little bit more, but to state the theorem, I require this condition. No, I don't know. Theorem is here. I don't give a proof, but it's just easy to compute. You substitute Fourier expansion to iterated integral and compute the integral term by term. Then automatically you can find this machinery and find a L function. So proof is almost trivial. Actually, the proof given by me and Choi is really complicated. The statement and proof is also complicated, but using this generating function, statement and proof is simplified much more. So the remark is left-hand side is defined for arbitrary S. So using this expression, we can do the analytic continuation of this script L function. And it's obvious, if you multiply this gamma factor and pi factor, both sides, you can get the expression of L function in terms of iterated integrals. So inversion formula is easy to see from this expression. So remark. Analytic continuation is done of L function on S is given by this formula. So in particular, the L function are L values here for all so from the definition, each variable is large enough, should be large enough for convergence, but after analytic continuation, this makes sense for arbitrary positive integer k. So after in the next second section, we want to consider the relation among these L values. But anyway, at this moment, so at this stage, we could justify the value of L values are defined. And one more remark is, so such values are linear combination, is a linear combination of iterated integral of this form, and vice versa, where all alpha and beta is a positive integer. Simplest example is if all alpha is 1, then left side should be I, 1, 1, 1, f. This is the iterated integral, is 2 pi I minus n to the n 1, 1, 1. This is true. For example. So space spanned by L value is same as space spanned by iterated integral from this relation. From this expression, the original L this script L is better than original L probably, but I don't expect the Euler product formula for this L. I don't expect. So this was the first claim of this talk. So in the next section, I want to discuss the relation among multiple L functions.
So, and this last formula is also a special case of your result with Choi, right? This formula
Yes.
1, 1, 1.
Yes.
So in general, can you get your full theorem with her from this easier theorem? Can one deduce it just by comparing coefficients?
Yes, the Pascal. So
So it gives a new proof also, because you said your old proof is quite complicated.
yeah,
This is easier, so this gives also a simpler.
yes.
Yeah.
So this gives a simplified proof, and all resulting Choi and me is covered by this theorem. So in this section, we set up the algebra generated by L values. Algebra generated by special value of multiple L function. So in classical case, minus 1. So in our notation, this was ISF. The special value at s equal 1 and k minus 1, where k was the weight of each modular weight of f. The special value at s equal 1 to k minus 1 is called the critical value of L function. Actually, essentially, this is special value of L function at s equal. So such a value is called critical value, and it is known there are linear relation among such special values. So in this special values, critical values, special value at are called critical value. So we try to find the analogy of this relation. Find analogy of such relation is called period relation. So I want to find the analogy of period relation. Critical value or period. So following is a set of my setup. Definition. The title of definition is period space. So for given weight and level, so for given space of Caspar, we define the period space denoted by P and N, P of N. Simply we denote by Pn. This is period space associated to the space of Caspar. Is defined by the Q space spanned by special value of iterated to integral. This is a complex number in general, where each argument alpha runs from 1 to k minus 1. and here F runs all space of cusp form, but with rational coefficient. This symbol means cusp form whose Fourier coefficient is rational. Q Fourier. The base field is rational. I'm not sure this setup is reasonable or not. Here, F runs all cusp form, but if you fix the basis, this is a finite dimensional vector space. If you fix the basis, then this space is generated by a finite number of these values. And this is a finite dimensional vector space. Trivial upper bound is dimension Pn. So here, alpha, each parameter alpha runs from 1 to k minus 1. So there are k minus 1 possibility each parameter. And if you fix the basis of this space, so if you denote L is the dimension of cusp form, then upper bound is L k minus 1 to the n. This is a trivial upper bound.
Pn is a subspace of R.
Subspace of C.
Subspace of C. Ah.
Yes, thank you. Subspace.
Why C? Why not R?
But IR or R depending on
Oh, because
parity.
you put some you include an I in your definition. But I mean, the usual definition, you would take out the I. These are real numbers.
Yeah.
Or pure imaginary, of course, because he's put an I. I mean, in the definition, the usual way would be f of it t to the s minus 1 dt. And then it's real.
Yeah.
It's more convenient. So,
Yeah.
so I mean, essentially, these are real. The power of I is
Yes,
Yeah.
essentially, yeah.
up to a
This
factor of I.
value should be defined on real value.
So
But
my question is that this is a subspace of R, and the answer is yes.
no, subspace of C.
Subspace
R,
of
in-
but it is not the subspace of R.
I times R.
because
I
you,
times R. Where
Mm.
yeah.
But that's just, I don't actually know why did you not include the I? Well, of course, it doesn't matter.
If you fix if you how to say, if you choose alpha to be some parity, alpha if alpha I is
Yeah, no,
different
I know
from
this very
parity.
well. I'm just asking why he didn't choose in his definition to include the I. To make everything real.
Ah,
That's
yeah.
the usual way.
That's
Just
right.
f of it t to the s minus 1 dt.
Yes.
Yeah.
Then everything is real, of
Yeah,
course.
yeah.
Of course, deep down it's a
Yeah, but
Yeah.
Conjecturally C minus and C plus is linearly independent over Q. You
Sure, but that's not a for classical multiforms, it's a theorem,
Mm.
a conjecture. But, yeah, no, I mean, people do both in the classical case. They use the pure and imaginary, real and imaginary, or almost real.
Mm.
Mathematically, I guess it's more natural to include the I, but it's easier to work with real numbers.
Mm. So my setup should be modified to
Well, I mean,
the
it's-
word.
it's-
Yeah, but
But anyway,
yeah.
it's not really in C, it's either in R or in I.
I
It's
times
some-
R times R.
it's
Ah.
a trivial power of I times R, so it's
But it depends on the how say sum of parity of sum of yeah. So
Oh, that's right, because you're mixing the parity also.
yeah.
Oh.
So
No,
sometimes
that's really
I forgot.
No, that is right.
Yeah,
That's
I
really
or
Yeah, equal parts, yeah.
depending on the parity
You're right,
of
that's fine.
0 or 1, what to do.
So you are mixing. So
Mixing.
so shouldn't be a.
Yeah, this is
not
more precise.
Each value is a real number or
I
pure
see.
imaginary.
Ah.
This is the- so
Yes.
It's much
Each
more
number.
natural. Why don't you put Pn plus or minus,
Mm.
and then if you put Pn plus or minus where the sum of the alpha i's is even or odd, you fix the parity then.
yeah.
I mean, it's really two spaces, and these two spaces are quite separate. You should never mix them, but of course you can.
So I should not write.
So you can define
Define, yeah.
real part, you can decompose into two parts.
Two parts, yeah, real part and the purely imaginary part.
And the real part.
Yeah,
Maybe some
yeah, yeah,
yeah.
yeah. So obviously this is a finite dimensional two-vector space. The trivial bound. In the case of multiple zeta values, so that gives conjectural dimension of this type of space found by zeta value. So I'm interested in the space of this space and dimension of this space. And one more definition. If you consider the direct sum of this space, this has an algebra structure. So this is period algebra denoted by P. Is just a formal direct sum of Pn. I'm choosing rational field as a base field. Then this has a graded pure algebra structure from the shuffle property. For example,
But just one. I mean, in the classical case, when all the CIs are one, then as we all know very well, there are two product structures. One by multiplying the iterated integral and one by multiplying the iterated sum. And they're different, and that gives the shuffle relation. So here, do you also get two ways to multiply or just one?
I couldn't catch you.
In the usual case,
Yeah.
multiple zeta values, when every CI equals one.
CI. Yes, of course, yeah.
In that case, we know that there are two ways to multiply zeta values, either from the iterated integral, the Greenfeld integral, or from the sum. And they're completely different, and the equality gives the double shuffle relation. So
Yeah.
my question here, do you also have two ways?
No.
Using definition 1 and 2, or?
No, we only have a
For the
shuffle
sum.
product for
For the sum.
integral. For integral. No.
Oh, right, the sum
Yeah,
one. for
because this-
C's and not, yeah.
Value is denoted by iterated integral, so only shuffle product holds. No harmonic product here.
No, but these are defined using iterated integrals, but you just gave us a theorem, the Q space.
Ah,
The
yeah.
space is the same as the one with the L series. You just told us that.
Ah,
It's your
but,
reciprocal joy.
L function has no harmonic product in this.
Exactly, yeah, there's no, because you didn't use that one as well.
So shuffle product means
Sure, yeah, no, it's clear.
if you consider the product I alpha 1 F1, this is an example. This is a single integral and single product of single integrals. Then there are obvious shuffle property here, F2, F1, like this one.
Sure.
This-
No, but for the L series, when you mentioned the L series, when you first defined, you said there would be a second definition.
Uh,
It's Cn instead of Cn.
Yeah.
And
Even
that one would have a shuffle product for the sum.
no. Still, that series has no.
If you,
I don't understand. Right? Maybe
Yeah.
I'm obviously getting stupid.
Yeah,
So if I simply multiply, for instance, tau of n over n cubed,
yeah.
and then I multiply, so this would be L of delta 3, and I multiply by L of delta 4.
Uh-huh.
So here I have n to the fourth.
Yeah.
Then obviously I can write this as n bigger than n plus
Yeah.
n less than n plus n equals n. N equals n is maybe a product. That's maybe the problem. N equals n get tau n squared over n to the 7th, maybe. That's the reason it doesn't. I mean, if you just multiply stupidly, you can put n bigger than m or n
Yeah.
less than n, but then we unfortunately have n equals n, maybe that's the can get tau n squared.
Yeah.
So that's why it doesn't work.
Yeah.
Okay,
That is-
thank you.
So, but this relates to the ranking
Yeah, of
L
course,
function,
but it's-
yeah,
yeah, it's no longer the original
Yeah.
function. So please erase this one.
Yeah.
I'm sorry.
Yeah. Thank you.
I couldn't do that in my head.
So for each space of Caspon, we defined algebra, Q algebra. Right. So okay, I don't know the answer, but the probably main question is what is algebra meaning, geometric meaning, or what's the meaning? Geometric or motivic. I don't know. So I want to state the one more theorem which gives the upper bound of number of algebra generator of this algebra for special case, in special case. So, okay.
Is it finitely generated? As an
No,
algebra?
no.
Well, because you said an upper bound for the number of generators, that sounded like it's a finite number.
No, a number of each grade, each degree n.
Oh, so not the algebra generator, it's additive, it's the dimension.
No, I consider the number of algebra generator in each degree n. Like
Okay, so modular products.
Yeah. So hereafter, we look at the special case of this setup. So I only consider the weight 2 case. So weight of modular form is 2. In this case, the definition of period space becomes simple because the parameter on upper line round from 1 to k minus 1. So when k equals 2 case, just upper parameter is always 1. And then you remember this is just L values up to pi factors. No, I forgot this side is pi 2 pi L. Minus n, I think. S2 and Q. And to state the theorem, so I need some notation. So there are some involution, so-called Fricke involution on this space. So this matrix gives some involutive action on this space.
-1.
Thank you. -1. Thank you. So we have a canonical decomposition, plus part and minus part. Upper plus, lower plus. And we define L plus minus is the dimension of S2 n plus minus. And then I can state the theorem. Let capital D sub n is a number of algebra generator of degree n. Here degree means number of iteration. Let be a number of generators, algebra generators, of degree n number of algebra
It's not
of
really very well.
of p s to n.
So, I mean, this is somewhat strange way to, right, because, so I think what you mean is simply it's the dn is the dimension of pn multiplied with the subspace generated by products pi times p.
Yes, yes, yes.
So it's just the irreducible part.
So dn is a dimension of p modulo p and degree n part. This.
D0 equals 0.
p0
D0, n equals 0. D0 equals 0.
is 0, 0. In the case of multiple zeta value, this sequence satisfies in the multiple value case 1 minus x to the minus dn becomes 1 minus x squared.
Number of d dot x.
Yes,
Number.
number is different, but yeah. Now we are considering the number of algebra generator, not dimension of vector space.
X to the n 1 minus x to the n
X
minus
sure.
dn.
Thank you, thank you. Yes. This is a case of multiple zeta value. So we're looking for the analogy of this setup. So note that this dn depends on the chosen space, Kasparov space, the weight and the whatever depends on. Then, so result is I gave a upper bound of this number and put, okay, this is the answer. dn bar is a number defined explicitly 2n times m prime equal m prime is odd, and mu is Möbius function, and l plus 1 l minus to the m negative l plus minus l minus to the m. Then dn bar bounds dn from above. For any small n and also capital N.
Plus minus.
The dimensions of
Oh, yes, okay.
plus or minus.
Mhm. So as a corollary, we can get the upper bound of the dimension of each period space as a corollary. If you, the small dn denotes the dimension of period space, Q vector space, dimension Pn S2n. Let dn and put dn bar by usual sequence. dn bar one minus x to the n minus dn bar. Yeah? Yes, yes. Then dimension of period space is bounded by dn bar from above for any n and n. So it is usually a number of algebra. If you know the upper bound of algebra generator, you can automatically get the upper bound of each dimension.
But what is the answer? I mean, you can insert the formula and undo the moves. You can give a formula for d and bar.
You want an explicit description of this one?
It should be very easy because
Really?
you've just this is the opposite of the Murphy's inversion you already did. It should be.
But I didn't compute. But
It should be.
yeah, it's possible. Yeah, I don't give a proof, but proof is almost same as a multiple variable case. But key point is this bound is may not best bound. So this is an important comment. Mark. This one and also this one. For some level n, probably this equation is not enough. It's proper equation appears. But in many or in some level n, by computer observation, the equals hold conjecturally or numerical observation says. In many cases, this inequality is equal. So as a comment, equal here may be true for many level n, but not all n. I checked numerically this computation. For example, when n equal 50 or 48, so my claim is en 1. At least level 15, 48, and 64.
48 is the smallest.
You.
But is it the first case?
Is it 40 or 50?
I'm sorry. Yeah, you can replace the order, but
No, but can you read this number? Is it 50 or 40? It looks like the 5 and 4.
50, 48, 64.
Is there some special order here?
Yes. In this case, the dimension of cast form is 2, and this is, in this case, dimension S2, 50 is 2. This case, dimension is 3.
So, genus of modular curve, you level.
Yes, I already checked the case, the space of cast form is dimension 2 or 3 case in the computer, so you can replace the order with him. So I will show you the result, computational result. But before show the computational result, as a comment, so to get the upper bound of algebra generator, we need a relation among zeta value, among L values. So I only use the shuffle product and the duality coming from Frick involution to prove this statement. So if L values has another relation not coming from such shuffle product or duality, then the upper bound should be reduced more. So as a comment, to give this bound, I only use shuffle product and duality coming from Frick involution. I can write down explicitly. In general, it is true. This value is the same. Alpha n, alpha 1, alpha fn. This one. It's easy to check by using iterated integral expression, just to give us the orientation of path 0 to infinity to infinity. Using only two relations, I could get the upper bound in the case of multiple zeta values, the generating function is quite beautiful, but I couldn't compute this type of generating function from this expression. Maybe use transform. Okay. So it should be possible. I compute the dimension of period space for small level. So in the last, I want to show you the table of dimension of period space. Table of dimension Pn S2n. So we have two parameters, degree n and level n. But so I only check the level n for n such that dimension of cusp form is 2 or 3. When n equal so first line express the degree, n is the number of iteration, and when level n is 22, 28, and 37, every case the dimension of cusp space form is dimension 2. In this case, the dimension of period space becomes this way: 1, 2, 3, 4, 5, 6. I couldn't compute here. 7. 1, 2, 3, 6, 10, 20. So even different level, the dimension of period space becomes the same numerically. It's strange or amazing. And in this case, the information of Fricke eigen is plus minus, no? Kappa becomes 1 case. In the third line, when level is 23, 26, 29, and 31. In this case, also same sequence appears. 30. And this is the case when, and this sequence is the same as D and bar. But we only have up to degree m, so everything is question mark. But there are one exception appears. When level 50, this is also case 02. But the dimension of period space is different. 2, 2, 4, 6, 12, 27. So, as I mentioned, when level is 50 case, this bound is not the best possible. Numerically, we have more relation. The relation comes not comes from duality or Shapley product. There are new relation. But now I know where this relation comes.
Well, it's not square free, and so you have a splitting, a Hecke splitting, which is different from the plus and minus.
No, but
In
you.
the case of 50, because it's not square free. Of course, 28 is also not square free. Huh. But it may be that the splitting is trivial. So when you have, I mean, if you just have S2 of gamma 0 of n, then in general there are just two Hecke pieces, plus and minus.
Mhm.
But sometimes there are many more. For instance, if you have many prime factors, you have many Fricke involutions. But you also have involutions if some square divides n, which I forget what they're called, maybe the U operators or something, like U5.
Mhm.
And so you can use them to make some further thing, and then you'll get. You see, the problem is that you're looking at S2 of n, but you should be looking at old forms and new forms, maybe.
Yeah.
So in the case of 50, there are old forms.
Yes.
25, but in the case of 31, so there aren't. So that changes everything, because of course the old forms and the new forms you should look separately.
Yeah.
So probably after you remove all sort of simple reasons from all the new forms, there won't be any reduction of dimension. Because if there were, you would find it many times, and you aren't finding it. So probably this dimension is always after you remove
So
kind of
this
trivial
extra relation comes from traditional result. So Dr. Anton suggested me. So actually S250 is standby to cast form, and we can choose F1, F2 is new form. I didn't explain today, but this is a special cast form. In that case, by Shimura's result, F1 ratio of such one becomes algebraic number. Shimura's algebraicity theorem, for example, now, once we know this is algebraic number, it's easy to find numerically. This becomes a quadratic number. So basically, this is a traditional L values of degree 1 has a relation, but over quadratic field. So after squaring this result, you get a product of a function, but you can expand the product of a function by shuffle product, and this becomes rational numbers. So this relation gives a second degree relation over rational fields. So L11, F11 equal minus 11. Yeah, this is square and shuffle. This is extras, comparing this one. And numerically, observation says every gap here is 2 more x relation and here 3 more x relation. Probably every relation comes from this relation with shuffle product in this case. But I think I also checked the dimension K3 case. In the case, I find more extra relation. Probably numerically, that relation never comes from the traditional relation of L function of degree 1. Probably they contain the relation which comes really higher degree, which only holds in the relation comes from degree 1. I believe.
I have a question. There is two new forms.
Yes.
What is the coefficient of new form? Is it rational coefficient or
Integer.
F1 and F2 are integer coefficient?
Yeah, if you write, I don't know general formula, but if you write the F1 is this way, then F2 coefficient has 3m times 5m or something. Just a parity difference. But in general, cast form may not span by new forms, so this is a really special case.
But,
The integer coefficient. So today I introduced the multiple L function and consider the special value of L function and consider the space spanned by L values, so-called period space. And the main result was estimation of number of algebra generator or number of generators as a linear space. And still, this I don't know where such relation comes, so research is in progress. But, thank you so much for a long time.
yeah, so
Thank you very much. Are there any questions, comments?
Question. If you, starting from your iterative integral, so in the classical case of multiple zeta values, there is a way of seeing the shuffle product inside the upper algebra of things generated by two generators as an equality containing a coproduct, so putting some proof-like condition. So here, when you start from a modular form, you've got these iterated integrals, and that you can write in terms of the generators of the modular forms of given degree. So is it possible or completely impossible in a direction to create an algebraic structure from these generators in which this shuffle product could appear as a coproduct condition, and such that your derivation ID also might work on them?
But generally, shuffle product is already Manin introduced associator. It's a generating function whose coefficient is iterative integral. And obviously, it satisfies the group-like property with usual coproduct. And he regards such associator as a generalization of period polynomial. In classical case, full modular group case, period polynomial satisfies the 3-cycle relation and 2-cycle relation. It corresponds to the relation with presentation of SL to Z. Many generalize such 3-cycle relation and 2-cycle relation in the case of associator in this setup. So, associator side is possible to
But then in your the derivation idea must be used here.
I'm not sure about that. Looks interesting. If you please.
If you consider principal congruence subgroup of level 2, then it is modular space of modular curve is P1 minus 0 and infinity. It is isomorphic too.
I guess.
In this case, is it same thing or different thing?
I didn't check the So this table is really small part of setup, right? We can choose weight and group.
I mean, the more obvious specialization, the first one to start would be level 1 at weight 12, so delta.
Yeah.
So in that case, one knows by Manin, that at least up to powers of 2 pi I, but the periods, the usual periods, although you said there are k minus 1 of them, so 11 in that case, 1, 2, 3 up to 11, but in fact there are only 2. There's only omega plus and omega minus, as we know very well, up to powers of 2, but I think the way you normalize that's exactly correct. So your space for n equals 1 would only have dimension 2, not dimension k minus 1. So already the upper bound is much smaller for n equals 1. So if you've done, that should be very easy to do calculations, for instance, for n equals 2 or n equals 3. Have you done that? So the corresponding table, just to, capital N is 1.
Yeah.
K is 12, so we're looking at delta, and little n is 2.
I compute the dimension.
And what do you get?
You mean period space degree 2, S12, level 1. Yeah,
and also P3 and so on. So what happens in this case? So P1 has dimension only 2.
Yes.
Even though the trivial upper bound, as you told us, was k minus 1 times the dimension, which would be 11. But 2 is much smaller than 11. So what happens when you go to n equals 2, n equals 3, and so on?
Oh. There are 121 values in this space, right? So
a priori, yeah. But in the case of n equals 1, there are 11 values. It's only two-dimensional.
Right, dimensional is, I forgot. I can check. But 14 or probably, I forgot, 10 or 14, I forgot.
No, but can you explain? Can you prove that? I mean, can you give the relations?
I think so.
It be very easy.
Proved. So.
He already looked at this case, I guess.
Yes.
But wait, now we're no longer talking about alpha equals 1, and therefore the L series is not, the L definition is not the same as the I definition. Right, you gave two different things. The iterated L series and the iterated integral.
I don't know.
They're not exactly the same.
not
Although maybe
same.
you said the space they generate is the same, so maybe it's not
Ah.
important. You said the space they generate for Q is the same. If you take alpha 1 up to alpha n or beta 1 up to beta n,
Yeah.
with I and with L you get the same space. You told us.
I don't
You
think
told us
so.
that. Well, you wrote that.
No, you mean
The vector space defined over Q is the same. You told us that there's an expression to go back and forth. Here. This is a linear combination.
yeah,
Q
yes.
and vice
You mean
versa.
L function and iterated integral.
Yeah.
Yeah, yes, it's
So
same.
it doesn't. So even though it's not the same numbers, it's the same vector space. I mean, in this case, it's the same numbers because it's just 1. Every alpha I equals 1.
Yeah.
So then it's the exact same numbers. But if we look at delta, then each alpha I goes from 1 to 11.
Ah,
So it's not the same numbers, but it's the same vector space.
I didn't check. I didn't check.
No, but that's what you told us. Isn't that what you wrote here? The space generated by the ulcers is the same as the space
Yes, same
generated
space.
by the iterator.
Yes, same
Same
space.
Q space.
But
So it's the
if
same.
you consider,
So the dimension is also the same. It's the same. Or not.
I think I should check more carefully.
So we put delta, delta, delta downstairs.
Well, when
Delta,
each
delta.
alpha runs from 1 to k minus 1, probably beta is running another range.
Oh, I see. They don't.
So if you only consider beta runs from 1 to k minus 1, and this, probably this space is different.
Oh, I see. So then you can ask your question for both spaces on the computer.
I only check this side.
But you could check the other because you have a formula for in terms of the I. So you can compute numerically, I think, all this. By the way, how do you compute these things numerically? By iterated integration?
Yeah, integration expression, but
Just numerical integration. So how do you do it when n is 7? You have a 7-dimensional integral? Or 6? I mean,
it
in
could,
this
yeah,
table.
it could using basically using iterated integral expression, but convergence near 0 is very slow. So I
But how
change
do you
that.
do the integral? By numerical integration? The 6-dimensional integral?
yes, using the Fourier expansion.
So not by numerical integration, for the, you insert the Fourier.
Insert the Fourier expansion.
So it's a sum, not a
Yeah,
integral.
yeah.
Okay.
So convergence speed at near infinity is quite good, but this is very slow. So using the Fourier
Use the
evolution.
frequency. Okay. But it seems the most natural question would be to take the case of delta, where we know that the dimension is much smaller for n equals 1 than it should be. And then you say it's something like 10 or 14, so that's much smaller than 121. But can you see why? Can you prove that, or is it just on the computer? Can you see what the relations are?
So already Manning gave
a...
a 3-cycle relation. So using that relation, we have a relation.
Okay.
But I didn't check. I checked that well.
That this gives the same dimension.
The same
Okay.
dimension.
So in other words, you have some relations, but you haven't checked that you get every relation, that you can prove every relation the computer shows you.
But
there are more relations than
I don't have enough data, or I only take the degree 2 case.
well, but even degree 2, that's 120 dimensional space, reduce it to 14 or
14,
or 10.
yeah.
That's
I gave
many
a conjecture
relations.
basis.
So you have 100 relations numerically, and maybe some of them can be proved, and some not. Anyway, it seems very natural case to look at. That's right.
Further questions? Oh,